All right, welcome to week 3. Last week we took a look at lists and tuples and talked about various characteristics of these data types. Both lists and tuples are iterable. They're also sequences, meaning that you can do indexing and slicing on lists and tuples. A list is mutable, meaning that you can modify the items that the list contains, whereas a tuple is immutable, meaning that you can't directly modify its items. Although it's nearly trivial to just create a new tuple with the same name as some previous tuple with different items in it. This week we're going to take a look at the two other important built-in container types, namely the set and the dict. Dict is short for dictionary. It's like a hash table. We're also going to see how to construct these various container types from each other, how to construct a set from a list or a dict from a list of tuples, and that kind of thing. Finally, we're going to take a look at what are called comprehensions, which is a very compact, concise notation that Python provides for creating lists, sets, and dicts. Comprehensions are an example of something that's thought of as Pythonic, which basically means that it's cool and means that it's something that you can do in Python that you can't as readily do in other languages. All right, so onward ho. A set is enclosed in curly braces in much the way the list is enclosed in square brackets or a tuple is enclosed in parentheses. The items in a list are unsorted and no duplicates are allowed. So a set in this way is like a mathematical set. The items contained within a set have to be what's called hashable. That is, each item has to have some unchanging computable hash value, and it also needs to be possible to compare the different items in the set to each other for equality. It turns out that the built-in low-level data types like int, float, bool, and str are hashable. And in fact, the hash value for an int is just the int value itself. The hash value for a float is just the float value itself, and so forth. And certainly these things can be compared to each other for equality. So all of those low-level built-in data types you can store in a set. A list is not hashable because it's mutable. That is, you're not allowed to store a list in a set because it's possible to change the items within a list. A tuple, on the other hand, is hashable if all the items that it contains are hashable. So if you have a tuple mixing together ints, floats, bools, strings, you can have that as an item within a set. However, if one of the items within a tuple is a list, that will not be hashable because the items in a tuple's list can be changed. Now this probably seems like it shouldn't work. A tuple we have claimed is immutable. Let's take a look at this particular example. If I say t gets parenthesis 3, 4.5, hello, and then a list 1, 2, 3, I have created a tuple. We can see that it's a tuple. It's contained in parentheses. I can ask for its type to confirm that it's a tuple. I can access an individual item and see that item. I can't change an item directly, so I could not replace the list at location t sub 3 with, let's say, some string. Here I get told that the tuple does not support item assignment, But the weird thing here is that the list within the tuple does support item assignment. So if I ask for t sub 3 sub 0, that is the sub 0 item from the list within the tuple t. That's a 1. And I can say t sub 3 sub 0 gets 123, let's say. And I have changed that item within that list within the tuple to 123. Good heavens, I've claimed that a tuple is immutable. So how is this working? Well, each item within a tuple is an object with an ID. That is, if I ask for the ID of t sub 0, I get some number. If I ask for the ID of t sub 1, I get some number. ID of t sub 2, I get some number. ID of t sub 3. This is the ID of the list. I get some number. Now, I'm not permitted to change these items to other items. I can't say t sub 0 gets 123. I can't say t sub 3 gets 3, 4, 5, 6. I can't change the list within the tuple t to some other list. That's invalid. But within the tuple, the list is mutable. And if I say t sub 3 dot append 19, let's say, that succeeded, t will show that that 19 has been appended to the end of that list item. However, if I look at the ID of t sub 3, I will see that this number is the same as the number that I got before. All right, so as far as Python is concerned, I have not modified the tuple. I have merely modified one of the mutable items within the tuple, and this turns out to be allowed. Consequently, a tuple is only hashable if each of the items within the tuple is hashable. If one of the items within the tuple is not hashable, and any mutable object, such as a list, is not hashable, then the tuple itself is not hashable. Okay, so now I've flogged the idea of hashableness to death. Let's return to looking at sets. Here's an example of a set. I'm saying S1 gets, and now I have a sequence of integer values that I'm going to store into the set. 1, 6, 5, 9, 2, 1, 6, 3. You'll notice that I have some duplicates in here. I have 2 1s and I have 2 6s. This is okay for defining the set, but those duplicates will be ignored. And when I now look at what S1 contains, I see that it contains 1 only once and 6 only once. So S1 is a set of 6 items, 1, 2, 3, 5, 6, 9. Now, you're going to look at this and you're going to say, oh, well, these are stored in sorted order. That appears to be true in this example, but I promise that items in a set are not necessarily stored in sorted order. They just happen to be stored in sorted order in this particular example. But as we make modifications to this set, or as we define other sets with other items, you'll see that they are not, in fact, sorted. Here I'm going to create a set S2 of different types of items. So the string high is one of the items. The tuple, 3.14, 2.72 is another item. And false is the third item of this set. Now this tuple is hashable because it only contains 2 floats, and the floats are not mutable. So this works fine. And it turns out in the output representation of S2, we see that it chose to put the bool ahead of the tuple of floats. Again, there's no guaranteed order for the items in a set. In this final example, if I try to say S3 gets a set containing a list 2, 3, and another set high by, this is going to fail because both the list 2, 3 and the set high by are mutable. All right, so mutable things are not hashable, and I get told unhashable type list. If I eliminated that problem, if I said S3 gets, and now let me just say 5, 123.4, and then a set containing high and by. Now, high is immutable, by is immutable, strings are immutable, but the set itself containing high and by is mutable. We haven't seen how to make modifications yet, but we will in just a moment. All right, so lists and sets are mutable. A set is also iterable. That means that you can step through the items of a set using something like a for loop. It is mutable. We are going to be able to add items to the set. We are going to be able to remove items from the set. And consequently, because the set is mutable, it's not going to be hashable. Now, unlike a list and a tuple, a set is not a sequence, so we cannot use the square brackets to subscript items within the set. We have S1 here containing these 6 items, but it's not going to be true that S1 sub 0 is a 1. That's just not valid. A set is also a collection, like a list or a tuple or a string or a range for that matter. That means that we can ask for the length of a set, which will tell us how many items the set contains. So len of S1 is 6. And we can also use the in and not in collection membership tests. So I can test 123 in S1, which is false, or 6 in S1, which is true. Or howdy not in S1, which is also true. Here on slide 5 are methods that we can use for modifying the items in a set. For example, I have S1. I can say S1.add, let's say a 12 to S1. Whoops, made a syntax mistake. S1.add 12 in parentheses will add 12 to the set. It appears that that was added in order, but I promise that's just an accident. I can say s.discard one of the items in the set. Well, I can say s1.discard, sorry about that, one of the items in the set. If I attempt to remove an item that doesn't exist, pardon me, if I attempt to discard an item that doesn't exist, that's simply ignored. Okay, so here I attempted to discard minus 123, and that was simply ignored. Now, another way of getting rid of an item from a set is remove, and remove is more particular. If I say s.remove 12, that's fine. The 12 is removed. But if I say s1.remove minus 123, remove is going to complain. I get something called a key error from remove. I can also pop an item from the set. Now, you may recall that for lists, the default for pop was to pop the last item from the list. But for set, the order in which things are popped is undefined. And consequently, you'll also notice that there's not an argument you can specify to pop indicating which one you want to pop from the set. All right, so if I say s1.pop, I happen to get the 1. If I say s1.pop again, I happen to get the 2. So now you'll see this and you'll suspect, oh, these things are being popped from the front. You cannot rely on that. All you can know for sure is that when you pop an item from a set, you will get one of the items from the set. And if you attempt to pop from an empty set, you will get a key error, just as we got from removing a non-existent item from the set. Finally, we have .clear that does the same thing it does with the list. That is, it wipes out all of the items within the set. And the way that an empty set is represented in Python is with the so-called constructor name set and empty parentheses. All right, well, I would like to get S1 back again. So let me recreate it. And what I want it to contain is these 6 values. Okay, so I have S1 back again now. These examples here repeat things that I've already just demonstrated. So you can step through these things yourself and see that they work. All right, so discard does not produce an error. Remove will produce an error if you try to remove something that does not exist within the set. We can use in and not in. We can clear the set with clear. If I do say s1.clear and then try to pop a value from the empty set, we see that we do get this key error. Okay, so those named methods allowed me to interact with items within the set. That is, I was able to add items and I was able to take out items and also check for the existence of items within the set. There are also the expected collection of set versus set operations. For example, the minus sign gives me set difference. That is, if I say some set 1 minus set 2, the result that I get is all of the items that are in S1 but that are not found in S2. S1 and S2 gives me the intersection of the two sets. The result of that is a set. The caret symbol is what's called the exclusive OR bitwise operator. This is borrowed or inherited, if you will, from C, C++, Java. In the context of sets, what it means is to give me all of the items that are in S1 but not S2, and combined with all of the items that are in S2 but not S1. That is, all of the items that are in one of the two sets but not both of the two sets. And then finally, the vertical bar symbol is the bitwise OR operator. And in the context of sets, that gives us the union of two sets. I can also test whether two sets are equal to each other, that is, whether they contain the same items or not. I can test whether two sets are not equal to each other. The less than and greater than symbols test subset relationships. So S1 less than or equal to S2 asks whether S1 is a subset of S2. On the other hand, S1 less than S2 asks whether S1 is a proper subset of S2. That is, in order for this to be true, all of the items in S1 have to exist in S2, but there also has to be at least one item in S2 that's not in S1. So S2 has to be a strictly larger set that contains S1 as a subset. And then, of course, the greater than or equal and greater than are analogous. These operators, by the way, all have lower precedence than set difference, set intersection, set symmetric difference or exclusive OR, and union. All right, so let me set up some sets that we can use for examples of these operations. S1 gets. I'll come back to you after I've successfully typed these in. Okay, so I've now successfully typed in these examples, set S1, S2, and S3. If I ask for the set difference, S1 minus S2, that's going to give me all of the items that are in S1 that do not exist within S2. So in other words, S1 minus the intersection of S1 and S2. The items that are common to S1 and S2 are 1, 2, and 4. So what's going to be left are these items, 5, 8, 9. And notice, yay! We finally have an example of a set that's not in ascending numerical order. All right, so I promised you that sets are not in any guaranteed order, and here we finally see an example. On the other hand, S2 minus S1 is the items that are in S2 that are not also in S1, and that turns out just to be the item 3. So I get a set with just one element, one item in this case. Set 1 intersected with S3 is going to give me the items that are common to both, and it turns out that that's just the 8 and the 9. The 8 and the 9 are the only items, the only elements that these sets have in common. If I ask for S1 exclusive OR of S3, that is, the items that are in S1 but not in S3, combined with the items that are in S3 but not in S1, I get everything except for the 8 and the 9. Okay? So the 8 and the 9 are common to S1 and S3. Consequently, this so-called symmetric difference, this exclusive OR of S1 and S3, gives me everything else other than the 8 and the 9. So I have 1, 2, 4, 5, and 6, 7, 10. Purely by luck, those do come out in ascending order in this case. Now, these operations associate from left to right. I think I forgot to say, so let me back up, that the examples that we showed here on slide 9 are in descending precedence order. So set difference has the highest precedence of these, down to the or union operator, which has the lowest precedence. And these operators associate from left to right within a precedence order. So here, it's perfectly fine for me to ask for the union of S1, S2, S3. These are evaluated from left to right, so first I get the union of S1 and S2, and then I get the union of that with S3, and of course the result of that is a set, S1 union S2, and the union of S1 and S2 union S3 will give me the items that are in S1 or S2 or S3. I can ask whether S1 is equal to S2, and of course it's not. They're not the same. I can ask whether S2 minus S1, okay, that's just the item 3. That's the only item that's in S2 that's not also in S1. And S2 minus S1 has to be a subset of S2. In fact, in this case, it's a proper subset of S2. So I can use the less than comparison, and I'm told that it's true that S2 minus S1 is a proper subset of S2. In this next example on slide 12, we're trying to detect whether the exclusive OR of S1 and S3 gives us the same set as the union of S1 and 3 minus the intersection of S1 and S3. Now that relationship should be true. That is, the items that are in S1 or S3 but not both should be the items that are in S1 or S3 minus the ones that are in both. But we're being told false, and the reason is because we have a precedence problem the way we've written this. All right, so let me type this out. S1 exclusive or S3, whether that's equal to S1 union S3 minus S1 intersect S3. Now the problem that we have here is that set difference has the highest precedence of all the operators, followed by intersection, then exclusive or, and then union actually has the lowest precedence among those four operators. So in order for this to work correctly, I'm going to need to use parentheses to force the association among these that I want. And what I want to do here is to compute the union of S1 and S3. That's going to be a set with all of the items in one or the other or both, minus the intersection of S1 and S3. So that's the items that are in both. So in other words, the items that are in either minus the items that are in both should be the items that are in either but not both. And indeed that's true. There are named versions of these symbolic operators that we've looked at. I can use dot union rather than the vertical bar symbol. And with dot union, I'm actually not restricted to only using sets. I can actually use arbitrary iterables. And my result, when I say S dot union of one or more iterables, will be the union of the elements of the set S with the elements from the iterables specified as arguments to the union method. This does not change the set S. It returns the union of S and the iterables. Let's skip ahead a couple of slides to take a look at an example of this union method. I'm going to define this set S1 to contain 1, 2, 5, 6. Then we'll execute S1.union, where the first iterable is the string high. Recall that as an iterable, the string is going to be split up into one-character substrings. The second iterable is the list, just containing the float value 3.3. Even though that list only has one item in it, it is still an iterable. And so when I ask for S1.union of high and the list 3.3, I get the union of the elements already in S1, that is 1, 2, 5, and 6, with H and I and 3.3. What's returned on my system is a set with the elements 1, 2, 3.3, 5, 6, H, I. So that's 7 elements, 4 from S1 and 3 taken from the 2 iterables. Notice that the order displayed here during my current session is different from the order of those elements that I got when I originally developed these notes. So again, I mean, there's no guaranteed order for the elements in a set. This method did not change S1 itself. S1 is still 1, 2, 5, 6. If I wanted to save a copy of that result of that union, I would need to assign that to some variable. So here I'm making the variable S2 refer to the union of S1 with those 2 iterables, and now I can keep track of that set using the variable name S2. Another one of the named set versus set manipulation methods is intersection. No particular surprise. If I say S3 gets S2.intersection, again, with intersection, I'm not restricted to just having sets as arguments. Here I'm using a range iterable, range 2 through 6, which of course actually means 2 up through but not including 6. And so S3 now contains the values from S2 that intersect with the values in the range from 2 up to including 5. And so the 2 and the 5 are the only elements that are common to both of those sets. In this case, the set S2 and the range 2 up through but not including 6. To make a copy of a set, we can use .copy just as we did for making a copy of a list. Here I'm saying S4 gets S3.copy. So although at this point S3 and S4 contain the same values and therefore compare equal, it's not true that S3 is S4. I get false when I test whether S3 is S4. Now, is S4 a subset of S3? Is subset compares just for subset, not for proper subset. So it's true that S4 is a subset of S3 because S4 and S3 are equal. These methods only work with iterables or sets. If I try to say S1 dot union the two values 9 and 10, well, here I'm going to get yelled at because 9 is not an iterable, 10 is not an iterable, and I get told int object is not iterable. If I wanted to create a union of the current contents of S1 with 9 and 10, I would need to create some kind of iterable containing 9 and 10. For example, I could create a set containing 9 and 10. A set is certainly iterable. And so here now I get the union of S1, which contains 1, 2, 5, 6, and this set that I've specified as my argument containing 9 and 10. Okay, now there are also updating versions of these functions that do actually modify the set to which they're applied. And other than to tell you that those things exist, I don't think I'll bother to show examples. All right, so that gets us to the conclusion of our discussion of sets. And next up, we're going to take a look at the Python dict, or dictionary. The other containers that we've looked at, list, tuple, and set, contain individual items or elements. A dictionary is different in that what it contains is key value pairs where the key and the value are separated from each other with a colon. So an item stored in a dictionary is this key value pair. The items are stored in the most recent Python implementations in order of key creation. So the first item that you add to a dictionary remains the first item, and so forth. You're not allowed to have duplicate keys. Like the elements in a set, the keys have to be hashable. Okay, so there are these restrictions on keys. Keys have to be unique. Keys have to be hashable. Items in a dictionary are stored in order of the key creation. There is no restriction at all on values. Values can be the same as each other or unique from each other. They can be mutable, immutable. A dictionary can have a key with a value that is another dictionary. There's no restriction whatsoever on the values associated with keys. Here I'm creating a dictionary named N to E. The idea of this is to create a mapping, if you will, from a user name to that user's email address. So name to email is what N to E is an abbreviation for. I'll go ahead and define this dictionary. All right, so my key has to be hashable. A string is hashable. So I can use John in quotes, as one key. And the email address for John is jkostlund@gmail.com. I'll type that in. Okay, so there's the first item in my N to E dictionary. The key is John, the value is jkostlund@gmail.com. Which works, by the way. That is an email address for me. Because I'm defining the dictionary in curly braces, I can go ahead and press the Enter key after a comma and just keep typing. My next key is going to be Al, and Al's email address is al@alcorp.net. And then I'm going to type my next item, which in this case is Bob, and he is Bob at basoc.com. There we are. So I have now successfully typed in the definition of a dictionary containing 3 items. The items are these 3 pairs: John and John's email, Al and Al's email, Bob and Bob's email. If I ask for the type of this object that I've created, I see that it is a dictionary. As another example of a dictionary, S to S stands for student to score, and instead of email addresses for values here, what we have is a list of quiz scores for each student. So my first student is Cal. I'm going to go ahead and just type this in and get back to you in a minute. Okay, so my student to scores dictionary also has 3 items in it: Cal, Dave, and Ed, and their scores for 3 quizzes. The scores are stored as a list, so each item consists of a string for a key with a list for a value. Ed's second item in his list is none. Probably Ed had an interview on the day of that quiz and hasn't made up the quiz yet. So none is a placeholder to indicate that there's no score there yet. A dictionary is iterable. It's not a sequence. So if I try to say something like N to E sub 0, I get nothing. The square brackets are actually used to look up the value associated with a particular key. And in my N to E dictionary, there is no key 0. There is, however, a key John. So if I look up the value associated with the key John, I see jkostlund@gmail. S to S, student to score of Ed, shows me Ed's 3 scores. And because that's a list, I can also do indexing on that list. So I can look up the list of scores associated with Ed, and in that list, I can use the index sub 0 to look at the first item in that list. So Ed's first quiz score was 94. If I try to look for a key that doesn't exist, as I actually already demonstrated here with 0, if I look for a key that doesn't exist, like N to E of Mary, then I get a key error. Adding new items to a dictionary is easy. You can use the square brackets to specify the key, and in this case, rather than looking up the value associated with psi, because there is no such value yet, we are going to define a value to be associated with that key. So psi at nou.edu will be the value associated with the key psi. All right, so N to E now has grown by 1 item. And in fact, I can ask how many items there are in that dictionary with len. You can see these are in key creation order. A dictionary is mutable, if I look up John in my N to E dictionary, John already exists. Perhaps I want to change the email address associated with that username John. All right, so here I am updating the value associated with the key John in this dictionary to jostlund@andrew.cmu.edu instead of the Gmail address. All right, so as far as basic sort of high-level properties, a dictionary is iterable. By default, it's iterable over keys. So if I use a for loop, let's say k in N to E, what I will get from the dictionary N to E is the keys of N to E by default. Okay, so the dictionary is iterable. It is mutable. As we've seen, we can add more elements to the dictionary. We can change values associated with existing keys in the dictionary. It's not a sequence, so we can't do things like slicing. The square bracket notation is used for dictionaries, but it does a key lookup rather than an integer 0 through whatever subscript. A dictionary is a collection. It's considered to be a collection on keys. So if you ask whether something is in or not in the dictionary, what you're actually checking is the keys. All right, here is my N to E, name to email dictionary. I can ask whether John is in N to E. That's true. Fred in N to E is false. If I look for Andrew, well, I have to be able to spell or type. If I look for Andrew in N to E, I get told false, because the only things that are being checked by in and not in are keys. We're not looking at the values or parts of the values within the dictionary. All right, so these examples here on slide 23 are similar to things that I've done. S to S is student to scores. The number of items, the number of key value pairs in S to S is 3. Dave is in S to S, but 100 is not in S to S. Now, there are a couple of scores of 100 in the value parts of a couple of items, but when we use in, we're looking for keys. Okay, so here on the top of slide 24 is another illustration of using a for loop to go through the keys of a dictionary. We can use the key that we found to access the dictionary itself from within the for loop. Here I'm saying for k in S to S. So this is for key in student to score. I want to print out the key and the last score that the student achieved on a quiz, S to S sub k, is the list of scores, and sub 2 is the last score. In fact, if I really wanted to be careful, if I weren't sure how many scores there were, I could say len of S to S sub k minus 1. Okay, I'm really pushing my luck there. All right, so the last score for the student whose key, whose name is K, is S to S sub K. That's the key value pair. Because the value is a list, I can look up a particular item within that list, and in this case, I'm saying I want to look at the last item in that list. And so if I remember to type my closing parenthesis at the end of print, I will be able to see Whoops. Okay, I really messed this up. Sorry. Let me quickly copy and paste this. My mistake. My mistake, as probably you noticed, is out here at the end of the print. The parentheses, this parenthesis character should be here. Okay, so s to s sub k, the length of that, -1, will give me the score, and I use my parentheses, and I'm all set. All right, well, I'm sorry for goofing that up, but there we are. You can entirely eliminate an item from the dictionary by using the delete command. If I say del of s to s sub Dave, then s to s no longer contains Dave at all. Dave and Dave's value have been eliminated. D.clear will wipe out all of the values in D, but leave D remaining. So if I say s to s dot clear, s to s still exists, but s to s is empty. Notice that open and close curly brace indicates an empty dictionary. S to S is a dictionary. Curly braces are also used to create a set, but an empty set is indicated by the notation set open close paren. Okay, so this is an annoying little tiddly difference to remember between creating an empty dictionary, which is just open and close curly, versus creating an empty set, which requires you to use the constructor name set with empty parentheses. I can make a shallow copy of a dictionary, and I can also pop an item from the dictionary. The order for popping items from a dictionary is well defined. The last key that you added to the dictionary is going to be the first key that's popped. All right? So I still have n to e sitting around, which has 4 keys in it. If I say n to e dot pop item, I claim that the last item is the one that should be popped, and it's going to be popped as a tuple. So rather than a key and then a colon and a value, I'm going to get a tuple containing the key and a comma and the value. So this is a key-value pair represented as a tuple. Now, one way to get the value for a particular key, as we've seen, is to use square brackets. So if I say n to e sub John, I get the value for John. If I say n to e sub Joe, I get a key error because there is no Joe in the dictionary. As an alternative, I can use the get method with a key, and that will never result in a key error occurring. If the key that I'm looking for doesn't exist, then what I'll get back by default is none, or I can specify the default that I would like to get back from get. All right, so rather than using square brackets to look for Joe, let me say d.get Joe. Well, let me say n to e dot get Joe, and I get back none. Well, none doesn't display, so let me show that what I got back was in fact none. As an alternative, I can specify something other than none that I would like to get. Pop is another alternative to the square brackets. Pop allows you to specify a default that you would like to get back if the key does not exist. If the key does not exist and you don't specify a default, you get a key error, just as though you had used the square brackets to look up the value for a non-existent key. Okay, so these examples here are similar to the ones that I've already done. I'm not going to repeat going through these. You can try them out yourselves. Okay, so here we're discovering that there are 3 items at this point in the N to E dictionary. If I delete one, there are only 2 left. I can look up Al with pop, and because Al exists, I don't get a key error. And at this point, because I've deleted John and popped Al, I've only got 1 value left, which is Bob. And then finally I clear N to E, and N to E is now an empty dictionary.